So I'm going to present a re-architecture we are doing on our search cluster at Salesforce. It's a big cluster. We have more than 10,000 machines. We are doing a re-architecture, and we are separating the compute, basically the Solr servers serving queries and indexing, from the storage of the cores. So my name is Ilan Ginzburg. I work at Salesforce in France, in Grenoble, on search infra. This is corporate stuff. You should not buy any purchase decision on what I tell you. But if you like what I present and you like this kind of projects, you can base the decision to apply for a job at Salesforce, right? 4 parts: general presentation, Salesforce, and our existing search implementation to explain why we're moving. The new paradigm of separation, few words on how we implemented it, and a conclusion. Salesforce is a company that is growing strong, very nice culture working in it. A lot of giving back with a very strong foundation called 1-1-1, 1% of workforce, 1% of the product, and 1% of the money goes back to the community. Because Salesforce is cloud-based, subscription model basically, we succeed if our customers succeed. And that's very important for us and for them. We are all in it together. And that changes perspective on things compared to I sell you this car and just go with it and I don't care. Here is a sample of some of the customers. Okay, now the real subject. What does search at Salesforce mean? So first, most important is that people are able to find what they're looking for. What they're really looking for, not what their query might tell us they're looking for. If you're searching for John Smith, you're working in a big supermarket chain all over some country, and you're searching for John Smith, and there are 2,000 John Smith. You are interested in a specific John Smith that is related to your branch, your activity, your supermarket, whatever. So we need to present you with a result that is meaningful to you. If your John Smith is number 1,700 in the result list, you have to, won't work. And we also have to support features like suggestion. As you type into the search box, you have suggestion you can click on before launching a full search. Synonyms for when you're spelling or spell correction. All this takes compute. It does not impact the size of the data, but it takes compute. Salesforce is also a provider of software as a service over the web. So we have multiple tenants, more than 150,000 customers, and their data needs to be isolated. Sony, I don't know if they're a customer, should not see the customer of HP, of Dell, or of Lucidworks. I don't know if any of these uses Salesforce. Because they wouldn't be happy and we would be out of business if that happened. So we need to be multi-tenant with very strict tenant isolation. Actually, we want no impact of the data of one tenant to another. Not even TF-IDF and things like that. And another thing is that there are many tenants, and we cannot control, we cannot know the evolution of their data or of their access patterns most of the time. It's not like a shop. You have you're selling shoes or whatever. You know Christmas is approaching, and you need to ramp up your cluster because you'll have more purchases online, stuff like that. Or you're going to import a new line of clothing, you need more data. We don't know that. We have to manage the things as they happen without really being able to anticipate. So that's for the data, that's for the access patterns. For example, one of our customers is in the commerce, and they have the green line, kind of green line. They have an average access volume all year long, and when Black Fridays arrives, there's a huge peak. And each customer has its Black Fridays at some other moment. For example, pay-per-view TV using Salesforce as for the support center. There was very important game. Many of their customers called their support. Huge peak of activity on the Salesforce side. And search has to deal with that. And the bars are showing that the volume of data a customer has on our systems and that we need to search on can vary at any time. A customer can start really small and during a weekend import millions of records into the system, and we have to accept. This is the current architecture. It's not based on Solr Cloud. It predates Solr Cloud. The tenant isolation is achieved by having cores that are customer specific. A core is for a single customer. A customer might have multiple cores when its data grows. The cluster takes care of itself as far as size and balancing of the cluster. Sorry, not size. As far as core size and splitting the cores and rebalancing the cores among the servers. This is automated, no human intervention. The cores split and they are moved between the servers to balance the occupation. As you see on this drawing, the cores are stored on local disks on the servers, local SSDs, which means it's not really easy to change the size of the cluster by adding or removing machines, servers. Because when you remove a server, you first need to make sure all the data will continue to be accessible elsewhere. And when you add a new server, it's initially empty. And you need to bring in data likely from other servers that are likely already overloaded if you need to add a new server. So the cluster size does change, but it won't change 3 times in an hour. We change it when we anticipate that the average is starting to grow or shrink. It's relatively static. We have 3 replicas for HA. And we are doing indexing for a given core on one of the replicas, on the primary, what was master versus slave. But when our primary for a core fails, we do indexing on another of the on one of the surviving servers, and this replication would be what I think would be called now pool replication. So it's not meant for doing that in pure Solr, because you might be losing data when a secondary becomes primary or a slave becomes a master. I'm going to describe a system to enable us to do that in a safe way. So I'm taking a scenario where we're going to switch indexing. We have 3 replicas, 3 copies of a core. The core is the bucket. Segments in Solr writes immutable files. Each time it indexes, it adds a layer of files. And we're starting from an initial state where the 3 replicas are identical. We have an indexing batch, writing segment number 3 on the bottom server. And as long as we write all our segments to this same server, they're going to be replicated to the other two and we're safe. But that server is unavailable for some reason, and the next batch is going to another server. So we see we have a segments are numbered in Solr. It's called generation, the number of the segment. So we have 1, 2, 1, 2, 3, 1, 2, 3. 3 is green on the top server and blue on the bottom server. So this is an inconsistency, and normal replication fails when it sees that, and we are losing some data. So what we've implemented using higher layers up the stack, higher than the cluster, is a failure detection using sequencing numbers of indexing, and recovery by doing a replay of missed indexing. This is handled by higher layers up the Salesforce stack, higher than the Solr cluster. So in the situation that I showed previously, where we indexed one segment on one server and another segment on another server, the system would detect an inconsistency, would do what it takes to reindex all the data on one of the servers, the new master, and we will end up with all, after replication has done its job, we'll end up with all the servers containing all the data. This is important because the existing implementation of storing in the Blob Store relies on that. Eventually it will be different, but today it relies on that. So, what are we changing and why? As I mentioned earlier, we want to store the cores, the shards, on a file system. Basically, Blob Store is stock S3, just a file system. I mean, if we were in AWS. And we want this storage to replace replication. So it's not that each server has its own space on S3 where it stores its data. It's that there is a single place in the Blob Store for a given core, and all the servers can go read from that place, and when they update that single place. It's a remote storage shared as opposed to remote but private. I mentioned that without the Blob Store, our cores are stored locally. So it's hard to turn off or add a server because of the data constraints. With this system, the cores are always accessible in the Blob Store, considered HA for its own sake. So it's much easier to turn off or to add a new server. We maintain 3 replicas for HA. At least with this system, we do not need to have a minimum number of replicas. We can go down to 0. If a core is not used, we can simply not load it on any server, because we know that when we need it, it's in the Blob Store, we go, we fetch it. And this is really related to the usage pattern at Salesforce I described earlier. We have thousands and hundreds of thousands of customers. Not all of them are active all the time. Business hours in the US, for example, make it that most of the data for US customers is sitting idle at night. We have demo accounts that might not be used for months, etc. being able to easily scale up and down the number of servers leads to public cloud efficiency because you pay what you use at any given time. We currently, most of our clusters are on private data centers. We have 2 clusters on AWS, one in Canada and one in Australia. Likely to be more, but don't base any purchase decisions. And high availability is made simpler because all we need to guarantee is that we will have a server, Solr server running and being able to load a core. We do not need to guarantee the availability by having copies of all the cores just in case the servers where the cores are failing. So it simplifies quite a bit. Oh, that's nice PDF. So ignore the big square. Just to put in context what layers of the Salesforce stack we are talking about, we are replacing the lower layer. What was the search cluster? We're replacing it by a new architecture of search cluster using a Blob Store. Previously there was no Blob Store in use. The upper layers of Salesforce and the search implementation. Here the search implementation is where you have the synonyms, spell check and all these things in addition to Solr. We will have to change a bit the cluster management layer, but we are really talking about the lower layers. Most of the search remains unchanged. A few words about the same, unless it's really something that is unclear, I'll take it at the end. Okay, thanks. The same issue I mentioned earlier with replication, where when we index on 2 different replicas, we might run into a problem that is corrected by our internal system. Same problem here. We see we have 2 yellow replicas that we took from the Blob Store. We try to index always on the same one. So only one replica pushes the updates to the Blob Store. When that server is down, unavailable, went into a big garbage collection loop, or for whatever reason, we can index on another replica. But then there is the risk we saw earlier of inconsistent data. So, maybe it's in the next slide. Yeah, it's in the next slide. It's in a few slides about updates. A few words on replication. Solr replication, which is a way for one server to get data present on another server. The replica that does not have all the data is on the left, and the Solr that did some indexing is on the right. And there are 3 primitives. One is asking the primary server, what version of the index do you have? Version is the generation, increases by 1 every time Solr does a commit. So this server can tell what version it's at. Then the replica can ask for what are the list of files composing the segments of that given version. It's like a directory listing of the current version, the current commit point. And the server would send a list of files. And then a list of files and their checksums. And then for each file, the replica can decide if it has that file, if it doesn't have that file, and it can go fetch all the files it needs to bring itself up to date with the copy, the more recent copy that's on the primary. It can compare the checksums. If it finds that there are inconsistencies, it can say there is no way to integrate the changes from the primary, and it can decide to throw away its own copy and adopt instead the complete copy from the primary. If the copies seem to be compatible, it just fetches what's missing. So replication is a dialogue, and the primary, if the primary is unable to open the core that the replica is asking for, it will not send it. So if that core is corrupt, the replica will not be getting it, which is kind of nice. So as we move from normal Solr with replication, our existing cluster, to one based on Blob Store, we have three principles. The most important one is we do not want to degrade performance. There will be some delay when a core has to be loaded from the storage. That's the law of physics. We are working on the speed of light too. There will be some impact here, but other than that, we do not want any degradation. So we did not go the way of mapping the Solr directory and other abstraction to go to a remote store. We want to go fetch the data. Once it's fetched, it ends up in the same SSDs where it is today, and no performance degradation. Second, and that's why I'm talking about replication so much, we wanted to build the exchange on replication, because replication code already exists, and if we can reuse it by adapting it, it's simpler than reinventing something. And number three, I mentioned that it could happen that we might be indexing on one server, then on another one. And in which case, we might have the two servers push their different updates to the Blob Store. Obviously, when you have a variable and two threads assign a value, x equals A, x equals B, you expect to find either A or B in X, but you do not expect to have the 16 most significant bits of A and the 16 less significant bits of B. And that's what is meant here by number three. When two Solr servers, if it happens that they push the same segment number to the Blob Store at the same time, once they're done, we want the Blob Store to be consistent, to have either the segment and all the files pushed by the first server or the second, but no mix. That's what it means.
So which do you choose? Which do you choose then?
If we compare, so in the previous slide, I said we want to build upon replication logic, the exchange between Solr and Blob Store. Blob Store, think of it as S3. It will be S3 if we're talking AWS. Replication, we have two servers negotiating. Blob push pull, we have one server talking to a file server and making all the decisions itself. So we can have logic on both sides, and Blob Store S3 does not know search. We are not negotiating with Amazon to put code. Replication is always asynchronous. In our case, it will be mostly asynchronous, but sometimes it will be synchronous. I'm coming back to this later. Okay, so sorry, this is Solr 4. It won't be Solr 4 in production. I run a test. On the left side, my local machine in the /index directory, and on the right side, the file names after pushing to Blob Store. I've listed all the file names related to the push of that core. All the files that have the nice arrows have exactly the same content, although the names here are unique names. It's not the same names. The segments.gen that is not completely useful is not replicated. And there is a very important file, core.metadata, that is present on the Blob Store and that is not present locally. And that's the file that we use to transform replication from a dialogue between two Solr instances to replication being a dialogue between a server and a file server. It's not really a dialogue. It's a bit like, if we open core.metadata, what do we see in it? We see a few fields with general information. The core name, skipping one, the generation, which is the number of Solr commits. The sequence number is the number I mentioned earlier that is used by Salesforce to track indexing and to make sure a core has all the content it is supposed to have. Unique identifier for this version of the file is corrupt, is deleted. Is corrupt is set to true when we detect a corruption, and that's a way to prevent servers from downloading a corrupt core. Given that we do not have replication where a corrupt core would not be served, we need to explicitly mark it so the server wanting to pull it from the Blob Store would not do it. Is deleted serves two purposes. One, when we delete a core, we do not want to do it synchronously to not slow down the delete operation that happens on the Solr server. We also need to propagate the delete to all the other servers. So when we do a local delete, we set this to true, and other servers looking at that core on the Blob Store know that they should delete locally because that core is gone and will be eventually garbage collected. So after this field, we have the blob files array, and that's very simple. It maps the Solr names to the unique names on the Blob Store, plus a checksum that allows, like we do in replication, I can compare, Solr server, can compare my local files to the files that are present on the Blob Store. I can compare the checksum to know if they're identical or no. And based on this array with all the files, I can decide which files I need to copy from the Blob Store locally, I need to pull. Or if there is a conflict, and I should be taking the complete copy from the Blob Store, for example. We have two other arrays that are empty in this case. One is for the config files, the elevation and the synonyms. There are none on this example, so it's empty. And the files to delete would be files from segments that are no longer part of the current index version, the current commit point. And we do not delete them as a segment becomes unused in the commit point, just in case other servers still access them because they opened a previous commit point and they're loading files from a previous commit point. And also not to slow down commits by having to do delete synchronously. I'm coming back, and this will answer your question about which version do we choose. When do we push? When does the Solr server push to the Blob Store? Every time there's a local change with a new commit and a new generation or a new config file, we are enqueuing in some local queue we've implemented, and asynchronously we're going to push that content to the Blob Store at some later point. It's a bit like replication, although it's a pushing initiative rather than initiative from the puller. This is pretty obvious. When do we pull? If a server that does not have a core receives a query for that core, it can go pull it synchronously, having the query wait in order to be able to serve it. If it gets an indexing batch and using the sequence number I described identifies that it does not have the latest version, it can go and pull synchronously the latest version available on the Blob Store before serving the indexing request. The rest of the pooling is just like replication. If you're familiar with replication, it's going to be the same way. A replica that is not the primary is going to either, it can periodically check the Blob Store and pull the updates, and that's what we've implemented. And we'll see later, if needed, we can have other channels to signal to a server it should be pulling updates through Zookeeper, for example, and getting notifications of updates. Of course, when a server is pulling from the Blob Store, it restores the original file names by reading the core.metadata and mapping the blob unique names to the local names. The deletes, as I mentioned, are all done asynchronously. So it's for files, for segment files no longer in the current index version. We add them to the array of files to delete, and they eventually get removed. Cores that have been deleted, we set the flag deleted to false, and they end up being removed. And we're getting to your question. The files, when two servers try to write conflicting changes at the same time, we'll see in the next slide, some files are written and not being tracked anymore, and we clean them up. It's really rare, so it's not a big deal. So, how do we manage? And so first of all, why do we have these unique names? So the strategy, it's going to be long. The strategy to write, to push new files to the blob, basically what we need to push when an update has happened locally, all the files that compose the new segments, and then the core.metadata that describes the new state of the core. We do not have transactions. We can be push transactions against S3. We can be pushing files. Things can fail at any time. We're never sure we're done until we're done. So the strategy is to push all the files, and once we are happy all the files that need to be written are written, we push the new version of core.metadata referencing the new set of files for the core. What S3 does tell us is that pushing a new version of core.metadata is atomic. So it either succeeds or fails. We either have the new content or the old one. So we're safe when we push the last one, the core.metadata. So why do we use unique names? Because imagine the first example of segment number 3. Imagine it was in a Blob Store context, and two servers start to push files for segment number 3 to the Blob Store. So let's say there are 5 files to push. They push each one its 5 files, and then each one writes core.metadata referencing the files and their checksum it just pushed. So one of the writes of core.metadata is going to happen after the other one because it's atomic. And basically the first one to write core.metadata, whatever it does will be lost. and the second server to write core.metadata will win, and that's the core.metadata will end up with. What we want at this point, even if the two servers were pushing even if the two servers were pushing the same files, we want all the files to be corresponding to the server that pushed the core.metadata. That's why we push unique names. Files that have the same Solr names will not overwrite each other, and the server that wins the race by writing core.metadata second is guaranteed to have a consistent core.metadata. So this does not guarantee that we have not lost an update, because obviously the data pushed by the other server is overwritten. It guarantees that we have a functioning core. And then we fall back to the Salesforce sequence number and indexing replace strategy. We see that the core, once we pull it back, or whoever is indexing next, see that something is missing, and we are going to do a replay indexing log basically, and reindex what was missed by the overlapping updates. So we are safe, like we are safe today. We are not causing corruptions that would force us to completely abandon the core and reindex everything if we are unable to open it. Numbers and conclusion. I stated earlier that this is going to make HA simpler for us because the cores are available. But if we do not maintain two replicas, when the server having a replica fails, we would have to reload that replica on another server before being able to serve the next query. This might take some time. I mean, it will take some time. Is this acceptable or not? Do we need to have two replicas always for this, or can we load it when we need it? So I took, on a non-Blob Store based, I took a busy search server at Salesforce at a busy time of week of one of the largest customers we have. And I looked at the activity and the number of unique cores accessed starting at 2 p.m. on Wednesday. And what we see in red is that in the first second after 2 p.m., from 2 p.m. to 2 p.m. 0010, 65 distinct cores were accessed. So if I imagine that we are in the Blob Store architecture and that server has crashed at 2 p.m. instead of, it won't be able to serve these cores during the first 10 seconds. They would have to be loaded elsewhere because it has crashed. The load time at the highest available bandwidth between an EC2 instance and S3, which is 25 gigabits per second, is way below 6 seconds given the average core size we have today at Salesforce. That means that these 65 cores could be reloaded in 6 seconds, let's say. So the delay on a query to any specific core of them is not going to be huge, and it might be acceptable. In cases where it is not acceptable, we will have the higher layers of the stack will have to maintain a hot or lukewarm, at least, replica so that queries can immediately move to another server. So it is an option to rely on the HA of the Blob Store to solve our problem. So zero. I have 0 minutes left. So 59 seconds. This code is being perf tested right now. Perf robust tested. We have a way at Salesforce to put code in production environment, production traffic without any customer impact, and that's the next step very soon. It's going to enter this. We're going to see how it behaves. This is then going to be the foundation for building a very aggressive elasticity layer on top of it, reducing the number of servers and increasing them on demand. And because of the very flexible way of loading the cores, it's going to be much, much easier to implement than anything where the cores are stored locally and need to be moved from server to server. It could be useful for other organizations if you have these needs. We have at Salesforce with very varying access patterns, both volumes and queries and indexing, changing over time. And open source, in its current version, it really relies on our ability to replay indexing. Future versions might make the write to the blob synchronous, in which case it would be easier to make it more widely available, and we might do so then. That's it.